Hello everyone, welcome back. So in the previous video, we understood how MOSFET operates. So qualitatively, we have explained what is meant by subthreshold, what is meant by linear and saturation regimes. So today, our goal is to get a more quantitative understanding. To do that, we will start with deriving an expression for the current in a MOSFET in the linear regime. Okay. Remember when we said linear regime, VDS was small, right? VDS was, let's say, about 50 to 100 millivolts. That's a reasonably small number that we use. So how do we derive an expression for current? To understand that, we need to notice a few things. That is, this is a schematic of a MOSFET. You see that there are the source and the drain regions. And when VG is greater than VT, you have the inversion layer which is formed here, okay, just below the oxide. And of course, MOSFET is a three-dimensional device. So along with the length, which is the distance between the source and the drain here, this is the length. You also have a second dimension which is going into the paper here, into the slide, right? Wherein that's the width of the MOSFET. We introduced that as well in the last lecture. So now if we want to derive the expression for current, what do we do? Well, we need to understand what is a charge density first. Current is simply charge density divided by time, right? Charge divided by time. So what is the charge density? To get to that, we will start with the definition of VT. VT was phi ms minus the equivalent interface charge divided by Cox minus Qd by Cox, which is a depletion charge, plus 2 phi f. Remember this expression we derived for MOS capacitors. So this particular first two terms, we called it as VFB, flat band voltage. Essentially, whenever you have non-idealities, the flat band voltage will be non-zero. Okay. And 2 phi f is a surface potential, which tells you how much is the potential drop across the semiconductor, right? And this is the oxide voltage drop. So the threshold, at threshold voltage, you have this relation that is satisfied. Now, if you increase VG above threshold, what happens? We said that there is a quick buildup of inversion charge right below the oxide, right? And it behaves like a parallel plate capacitor is what we said. So we can write an expression for VG just above the threshold, okay? So when I say VG now, there will be this VFB, which is again the flat band voltage, which is anyway there, minus QD plus, I would say, Q inversion now by Cox. So there is an additional inversion charge, okay, right below the oxide. That's why I'm adding that inversion charge into this, plus 2 phi f, right? Surface potential doesn't change. Surface potential reaches the maximum value of 2 phi f and it stays there. That's a delta depletion approximation. Okay. In reality, there will be a small change which is negligible anyway for our purposes. Okay. So this I can again simplify as simply VT minus Q inversion divided by Cox. Only the Q inversion term I'm adding, so I'll just take it out separately. So rest of it is all VT, right? So now, because of that, I can rewrite this expression as, this implies, I want to write expression for Q inversion, okay? So Q inversion is the inversion charge density, which is equal to minus, I'll write it as Cox into Vg minus Vt. Okay. This is a very nice and elegant expression. So compare it with the parallel plate capacitor. So in a parallel plate capacitor, we know that Q equal to CV, right? So if you apply a voltage V, you will get a charge Q, right? Capacitance is C. Similarly here, Vg minus Vt is essentially the excess gate voltage, I can say. Excess gate voltage or basically gate voltage over VT. Okay. If I apply that, essentially I'm going to get a charge, inversion charge, which is proportional to, which is equal to the capacitance Cox times the excess gate voltage. So that's a very nice and elegant expression. But remember, this charge is basically farads per, sorry, not charge. Cox here is farads per centimeter square. So your charge is going to be coulombs per centimeter square. Okay, it's a density, charge density. Okay. So this is if your Vg increases, of course, your Q inversion is going to increase proportionately, is what it is saying. Okay. So this is a very nice expression for us to calculate the total inversion charge density. Okay. So now what is ID, the drain current? Because you have this inversion charge, which is if your VDS is low, it is more or less uniformly distributed, right? I mean, the density doesn't change with position. But now, so the current will be ID will be simply the charge, total charge, divided by the time it takes for it to move from, let's say, from source to the drain. Okay. So I write the current as the charge density Q inversion, which is, I'll drop the negative sign because that can be taken care by the sign convention. I don't want to explain that now. Okay. Eventually, for drain current, the convention is that the current comes out of the drain because electrons move into the drain. So current comes out. So that is taken as positive. Okay. So we can write this as the charge density, which is simply Vg minus Vt times the area. That is the total amount of charge which is there in inversion under the oxide. So the total area is equal to simply width times length. Because length is the distance between source and drain, and then into the plane of the slide you have width. So the total area of the active region of the transistor is going to be W into L. Not active region, I shouldn't say active region. The total area under the gate is going to be W into L. And that is going to be divided by tau. Tau is simply the time it takes for electron to travel from source to the drain. And how much is tau? Well, tau is simply going to be equal to the distance, which is the length of the transistor in this case, divided by the velocity. And what is velocity? Remember in the drift, when we discussed the drift phenomena, we said velocity was proportional, velocity was equal to mobility times electric field. Okay. You have to go back and look at, if you forgot this, just go back and look at the phenomena of drift we described. Okay. The units also will be consistent. You can check out that, electric field, write out the units, and mobility units, that should give you velocity. Okay. And what is electric field now? Electric field is simply the voltage applied divided by the length, right? So the voltage applied is VDS between the source and the drain. The distance is L. So I will write this as L square divided by mu times VDS. Okay. So this is the time it takes for the electron to go from source to the drain. Now I can substitute back into the expression here on the top, right? And so I will get my drain current ID equal to mu and VDS will go up, and there will be an L square in the denominator that will cancel out with one of the L's in the numerator. So it will be mu Cox. I'll write it as W by L deliberately. And then VGS minus VT times VDS. Okay. So this is the expression for current in linear regime when VDS is small. Okay. You will see in a moment that this will not hold true when VDS is large. Is it dimensionally correct? Let's check it out. Okay. What should be mu? Mu is mobility, which is simply centimeter square per volt second. Cox is farads per centimeter square. W and L are length units, so they'll cancel out. You don't need to worry about that. And then this is voltage square. Voltage VGS minus VT is voltage, and VDS is voltage, so voltage square. So what you get is centimeter square goes out. One of the voltage goes out. So farads is C. C into V is Q, charge, right? So this is coulomb per second. So well, this is current, correct? So dimensionally we are satisfied. So coulombs per second, which is current, amperes. Okay, so dimensionally we are fine. So what does this expression tell us? If you look at it, current seems to be proportional, okay, current is directly related to the gate voltage and also the drain voltage. Okay, if you apply greater amount of drain voltage, you get larger amount of current, which is not surprising, right? And if you increase the gate voltage, you're increasing the amount of inversion charge which is present, so you'll have larger amount of current. So I can plot out, or rather, I'll define R linear, okay, resistor. Okay, I'll denote this in a separate section. So R linear, I'll say simply VDS by ID, which will turn out to be, if I take it, so it will be 1 over mu Cox W by L Vg minus Vt. If you want to be explicit about it, you can write actually VGS, simply to say that Vg with respect to the source. Okay? There's not much of difference between Vg or Vg minus. Just explicitly we are mentioning that. So what does this tell us? It tells us that if you see you take a MOSFET in the linear regime, that means you plot VDS versus ID, you get a current, which is, the relation is linear, and you get a curve which looks like this. Let's call this as VGS1 at some gate voltage. That has to be above threshold, remember. If you're below threshold, it's going to be zero, flat. That is, if you are below threshold, it has to be like this. As you increase the gate voltage, it goes up. Now, if you take an even higher gate voltage, you're going to increase the amount of inversion charge. Because of that, the resistance drops. And so if I take another VGS, this will be VGS2 greater than VGS1. So the resistance drops. Because of that, at a particular VDS, you have current increasing. Okay, so as VGS increases, current increases. Okay, this is the linear regime of a MOSFET. Okay, so we didn't really do much in this. We just understood what is the relation between the inversion charge and the gate voltage, and from that we derived the expression. Okay. But towards the end of the last lecture, I mentioned that if VDS is substantial, if VDS is large, then we are entering the saturation regime when there is something else that happens, right? So what we said was the channel gets pinched off. Well, some of you might really not be very comfortable with pinch off even now, because it takes a little bit of time to appreciate it. Okay. So what we are saying is, if you have a MOSFET, let's say you have the source and the drain, and then you have a oxide which is there on top, and now this is gate. Let's say VG you are applying. Okay, and let's take an example and say that this is equal to 1 volt. Okay. Now, when VDS was 50 millivolts, a very small number, right? Essentially, the difference between source and drain is very small, right? But now let us mix it up a little bit, and let's say I'll apply VD equal to 1 volt, almost comparable to the gate voltage. Then what happens? What we said in the previous lecture was that as VD increases, it's essentially a piece of semiconductor. So voltage has to drop across that, right? So How will the voltage drop happen? Let's, for example, let me take, let's say we know that this is anyway grounded. That is anyway given to us, right? So let's say at this edge, my voltage was 0. Let's say somewhere in between it is 0.25, somewhere else it's 0.5, 0.75, and 1 volt when you come to this. So essentially what we're saying is there is a variation of voltage across the channel, and which we called it as Vx. So this is basically Vx, which is variation of voltage across the channel. Now, if you want to create inversion charge, what is the voltage required on the gate? How much, we already saw that the inversion charge is essentially excess gate voltage, right? I mean, gate voltage above Vt. If your gate voltage is below Vt, you don't have inversion charge. Now, what is happening is, in the linear case, the variation across the channel was nothing. It's negligible, so we took it as 0 and we took a uniform charge density. But now, there is a variation of voltage across the channel, so we have to talk of what we can call as VGC. Okay. VGC means I'm taking voltage at the gate minus Vx. So at each point on the channel, I have a different voltage because it's just behaving like a resistor, right? There is some amount of resistance. It might be large, it might be small, whatever. You have some resistance there. Okay? And so this VGC has to be greater than Vt. If it is or greater than or equal to, let's say, okay, what happens if it's less than VGC? Then there is no inversion charge, okay, at that location, right? And because of that, we have drawn this picture in the end, towards the end of the last lecture, wherein we have shown you have this sort of a thing. Okay. We can say two scenarios. One is if I take this to be my drain and this to be my source, and this red curve should be when VDS equal to VGS minus VT, which I'll call as VDSAT, okay, saturation voltage, saturation drain voltage. So if you reach that point, VGS minus VT, what happens to VGC? You can substitute and see that VGC will become exactly equal to VT. Okay, when you are at VDS equal to VDSAT, then VGC will be exactly VT. That is why you have very, almost negligible inversion charge. Okay, and if you go beyond that, okay, for this black curve, this is basically VDS greater than VDSAT. If you do this, the channel is getting pinched off. You don't have sufficient voltage. If you calculate VGC now, VGC is less than VT. So no inversion charge near the drain end. But we still have substantial amount of charge, already, right? Because near the source we have a charge, and that is what is being depicted by this sort of a variation. So even in this is another picture from Streetman, essentially showing you that as you approach the drain side, there is a drop in the inversion charge density. Okay. See, this is this can sometimes be misleading. This doesn't mean that in space there is a distribution. It's still inversion charge right under the interface, but the density is different. Okay. You could probably depict it by a color graph, but yeah, this is what usually we do. Okay. It is simply telling you that density is varying, not the physical distribution. Along the y direction, it is still the same. Okay. Okay. All right. So now when we have this sort of a variation of potential across the channel, how do we calculate the current? Okay. And to do that, we employ what is known as a gradual channel approximation, essentially saying that the voltage across the channel is gradually changing. And in the picture below, we are showing that there is some sort of distribution. X equal to 0 here, in this case, would be the source, and X equal to L will be the drain. So between source and drain, there's a distribution of voltage. Okay. As a first approximation, it can be linear, but well, the accurate one turns out to be this, gradual, some sort of a quadratic relation. Okay. So now, what happens? What does the gradual channel approximation tell us? It simply tells us that there is a variation of inversion charge across the channel. So now in the linear case, it was uniform, right? Density was uniform everywhere. But now there is a variation in the density. So Q inversion is actually a function of X. And also, this is kind of subtle, but it assumes that the gate voltage in the normal direction, that is from the gate to the oxide to the semiconductor, that Y direction, in this picture here, Y direction is basically depicted here. And this is the X direction along the channel. Okay. So what it tells you is that in the Y direction, whatever you have gate voltage, that field is much stronger than the field across the channel. Well, it's a very reasonable approximation. Remember, what is the gate oxide thickness? Maybe, 10 nanometers, 5 nanometers, right? So the fields are going to be very, very large compared to channel lengths, which are maybe tens of nanometers, right? So when you compare with the channel length, it's definitely true that the vertical field, across the oxide is much more stronger. Okay, so this makes sense. It's important because we are kind of neglecting the horizontal field. And if you actually have to do it accurately, we have to take both fields into account, and then it becomes more complicated. We have to do it numerically. We can't do it analytically easily. Okay. But anyway, this seems to be a reasonable approximation, especially when channel length is long. Okay. So we will discuss about what is long channel, what is short channel, down the line. But traditionally, the channel lengths were microns, 10 micron, 5 micron, 0.25 micron, and so on. Okay, we will discuss more about that. Also, we are assuming that there is no leakage from the gate oxide. Well, that is an ideal, silicon dioxide, right? Ideal insulator. We are assuming that is still holding true. If not, we will have some trouble. Okay. And of course, carrier mobility, we are assuming that it's a constant thing. In reality, it doesn't turn out to be constant. There is some dependence with the gate voltage, but for our purposes right now, we will neglect that. Okay. So fine. So with the gradual now, this is the gradual channel approximation. And how do we, what is the current now, drain current? The way we can derive it is, we will follow the similar approach, but we'll make one small change. Now, drain current was, we said Q inversion divided by the time taken for it to travel, right? The charge to travel. Now I'll say that Q inversion is not a fixed number. It's a function of position. And how do I capture the variation of inversion charge density as a function of X? Well, I'll write it as, I'll include Vx term. Okay. So I'll say this is equal to Cox Vg minus Vt. In addition, we are saying now there is a Vx term. Vx equal to 0 at the source end, but as you go to drain end, it becomes equal to Vds. Okay. And then W into L divided by tau. Tau is the time taken for the carrier to travel from left to right. And what is that equal to? Well, we have seen that tau equal to, okay, maybe I'll just use black. Tau equal to L by V. Okay. And this is going to be equal to L by mu times E. But now electric field is not a fixed number. In the previous case, we have taken electric field to be VDS by length. But now we are seeing that the electric field is going to change, because there is some sort of a nonlinear distribution of voltage. So electric field now will turn out to be dVx divided by dx. It's not VDS by L like in the previous case. Okay. We'll substitute this. If you substitute this, what do you get? Well, you get mu Cox W Vg. Okay, I'll make it explicit. I'll say VGS, just simply saying that it's reference to source, minus Vt minus Vx dVx by dx. Okay, then ID. This is equal to ID. Okay. Now what I'll do is I'll integrate both sides. I'll take dx to the other side. I'll say integral of ID dx. I'll integrate it from 0 to L because I have ID, which is the field which is slightly different at each location. So if you want to compute the total current, you have to do an integral. And that should be equal to, I'll take out mu Cox W integral of 0 to VDS now. Vx is changing from 0 to VDS, right? VGS minus VT minus Vx into dVx. So this will turn out to be mu Cox W VGS minus VT times Vx minus Vx square by 2. This will be 0 to VDS. All right. So if you substitute the limits, and on the left side you have 0 to L, so I'll take the L on the other side. So if I do that, what I get is ID equal to mu Cox W by L VGS minus VT times VDS minus VDS square by 2. Okay, so this is the square law current. No, square law theory we say. Okay, what it tells you is current varies as the square of voltage. Okay, there's a small correction here. Okay, let's understand this a little bit more. What happens when VDS is small? Okay, when VDS is small, second term is negligible. This implies you have the linear approximation, right? We have already seen this linear regime, linear approximation for current. Right. We have derived this. We get the same expression. So that's sort of a validation for us. Okay. What happens as you increase VDS? As we increase VDS, we said that we get to a saturation point. Okay. That we define it as, in the textbook from the, the figure from the textbook, it is defined as VDS sat, which is VGS minus VT, or sometimes we can also refer to it as VD sat, saturation voltage. Okay. So you have two regimes. One is the linear regime. As you go to larger and larger drain voltages, you get saturation, and then the current remains flat. It doesn't change. Okay. And if you use larger gate voltage, the current increases. This is VGS increases, current increases. Okay. This picture is not quite accurate. We'll have to this is simply a qualitative picture. We'll have to correct it. I'll actually show you an exact number, that exact drain current that is calculated for a 0.25 micron technology in a moment. Okay. So this is a square law. Let's analyze that a little bit more. Okay. So what I'll do is I'll again take this expression. Okay. And now what we are saying is, if you just purely look at this expression, how will the current change with respect to VDS? Okay. So take a moment and think about it. So let's try to plot ID versus VDS just based on the equation. What does it tell you? When VDS is small, the current increases. Okay, that's good. I mean, we like that. But as you go to VDS higher than VD sat, then the second term takes over, right? If you just purely look at the expression, this is VDS square. This starts becoming dominant. And this becomes dominant, the current starts reducing. Okay. So if you look at purely the expression, the current should reduce like this. Okay. Which is not what actually happens. Okay. So when we write this expression, we are implicitly saying that this is for VDS less than VD sat. And what is VD sat? Just once again, VGS minus VT is VD sat. Okay, this is equal to VD sat equal to VGS minus VT. Okay. If your drain voltage is less than VD sat, then this expression is good. But if your drain voltage is greater than VD sat, okay, what does this expression become? This expression becomes ID equal to mu Cox. Oh, I'm sorry. Mu Cox W by L into VGS minus VT times VD sat minus VD sat square by 2. Or you could actually substitute it back and you can write it as mu Cox VGS minus VT. VD sat is VGS minus VT, so I can write it as whole square. And there's a half, next to the second term is half. So basically this will become 2L. There's a W, okay? So this is my current expression for a MOSFET in saturation, okay? So this is ID in saturation. So that, and you see that as you increase the gate voltage, the current is increasing in square, right? Current increases as a square of gate voltage. That's why we call it the square law, okay? So the theory predicts that you should have a drain current like this. And if you increase gate voltage, let's say by equal, let's say I'll change it from VGS equal to 0.5 to 1 volt, then my current should increase by, saturation current should increase by 0.5 square, okay? So gate voltage squared is how it goes, okay? That's why it's important, okay? And in this, you have many, many parameters. Well, it turns out that, mu Cox and W by L are essentially the design parameter. I mean, mu and Cox are the process parameters. W by L is what we can design. Okay. So the whole thing is, kind of fixed. So we will call this as transconductance parameter. Okay. We will discuss that in greater depth next week or next lecture maybe. Okay. So this is what you have. Now, let me take an example. Let me try to calculate what happens to the drain current. Okay. I'll take a simple example. Then after that, I'll stop this video and then I'll continue in the next video. All right. So ID, I can write it as simply kappa times VGS minus VT times VDS minus VDS whole square divided by 2. Okay. So I'll ask you, you know this expression, we have studied this now. So I'll ask you to calculate the drain current when, let's say, kappa equal to 1 amps per volt square, VGS equal to, or rather, I'll give you VGS minus VT equal to 0.5, VDS equal to 1 volt. I'll give you this expression. Then I'll ask you to calculate. Many a times, whenever I teach a course of, let's say, 50 students or 80 students, at least there will be 5 to 10 students who will do this. What they will do is they'll substitute. So ID is going to be 1 into 0.5 minus 1 divided by 2, right? So 0.5 equal to 0. They'll say there is no current which is flowing in the MOSFET, which is not true. Okay, this is a kind of a small trick question. We should remember that now VD S is greater than VD sat. So we have to change the current expression. We have to take VDS, we have to say ID equal to kappa times, you can take 2 here, and VGS minus VT whole square. Okay. I think if you do this calculation, VGS minus VT is now 0.5. 0.5 whole square will be 0.25 divided by 2 will be 0.125, 125 amps. This will be the correct drain current. But many a times I'll always find, students who will actually give me an answer 0. Answer 0 is going to be wrong. Okay. So this is what square law is. Okay. And we will solve a couple of more examples, and we will discuss how NMOS and PMOS devices differ in the next video. So I'll see you there. Thank you very much.